It'll be useful.
Call is now being recorded.
Okay. So what is the purpose of student presentations? So here's the reason. So this is specifically for the first years. Why do we do student presentations? This is not a part of your MBA syllabus. You're not going to get marks for this or something. We will be basing your internal marks based on your performance on student presentations, but it's not like a course you have to complete. So why are we doing this? Give me a second while I let people in. So why am I doing? So why are we doing this? Because in your life, at some point of time, you're going to have to do something. You have to do something which is going to be equivalent to a presentation. Okay. Yesterday and today, you sat through a bunch of presentations. Yesterday, Yadika ma'am did a presentation. Today, I've sat through 2 presentations. And all of these presentations that you saw today were done by students. So at point of time in your own college life, you might have to give a presentation like the guys from ETC and Enactus did it. But that's fine. Maybe it's once in a while, it's only if you're like a president of some cell or something. It might not happen to you. Fine. But many of you want to do masters, or you want to do some sort of, you want to do masters, and you want to go to college, you want to do PhD, you want to do higher education. At some point, I will guarantee you, you are going to do a presentation. Most likely for your master's dissertation. You're going to have to present it in front of either a committee or in the entire department. You're going to have to make a presentation and you can take questions. In some places, your presentation is going to be like a job interview. We recently had someone come in for a job in Salvation College. They had to do a demo class with actual students there. That is a presentation scenario where you have to give knowledge, where you have to like sort of put forward knowledge and take questions from the audience. Your interviews that you did in your first year to get into Salvation College is also a presentation scenario. Again, you're presenting yourself and your knowledge of something, and you're taking questions. Later on, even if you don't do academia, whatever, you decide to do a job in many companies, if you want to get something like a promotion or you want to get a higher salary, sometimes you need to do a presentation or a sort of a meeting where you have to justify why you want that higher salary, or you want the raise, or you want a promotion. Sometimes you have to make a presentation for that. At some point in your life, you're going to be in a situation where you either have to make a presentation or you're going to be in some sort of presentation scenario, like an interview. And at that point of time, the last thing you want to do is go, I have never been in a situation like this before. I do not know what to do. This core class, this idea behind student presentations, is to prepare you for a situation like this in the future where the stakes don't really matter. Okay? If in this student presentations, if you mess up, you make a mistake, you forget something, something goes wrong, that's fine, right? It's just a student presentation. We are just doing like classes for you to practice. At the end of the day, later on in life, when it actually matters how you do a presentation and how you comport yourself, when things like that actually matter, at that point, at least you can be like, hey, I did this all the time back in college. I did this once in college. I sort of have an idea of how to proceed, how to prepare myself for a presentation. That is the fundamental idea. It's to prepare you for something that in this day and age is something that is most likely going to happen sometime in your future. All right. So that is the general idea behind why we do student presentations. More specifically, these are going to be tailored towards how we do presentations in science, which means we are going to present on a scientific topic, which is a topic in physics. You're going to be expected to write an abstract before the presentation, just like I did. I shared the abstract of today's presentation with you. You're supposed to format the presentation in a specific way, and then at the end, you're supposed to take questions on the topic, right? So that is how a presentation is going to work. You guys are going to pick You're going to pick 2 topics. We will let you choose. We will tell you which one you can give your preference, but we'll tell you which one to do your presentation on. You're going to write an abstract about what material you're presenting. You're going to create your presentation. You're going to do your presentation, and then we are going to have some back and forth with question and answers. And in the end, we're going to create your presentation. Okay, that's going to be like a science thing, but in general, it is just to prepare you for the upcoming, for whatever presentations you might have to do in the future. Unfortunately, because of the online mode, we'll also be sort of part of this demo class. I'll also be talking about how you can make a presentation, how you format your abstract, how you format your references, some of the things you can do in preparing it. Unfortunately, because we're in online mode, there are a few other things that I can't talk about as well. For example, I can't talk about how you do body language and how you present how you stand in front of an audience and you do and you maintain like eye contact and things like that. That you can't really do in an online setting. Hopefully we'll have to do it. Hopefully we can do it sometime in the future. Now for this one, I have created a Moodle course page for my seniors, second and third years. The old Moodle course page is still available. Your guys are still enrolled in it. I just created a new one to reduce the clutter. Okay. So this is a new Moodle course page. Every presentation that's going to be done, it's going to be recorded. It's going to be uploaded on YouTube. I'm going to put the link over here. Okay. So later down the line in the future, you actually have proof that you did a presentation. You can put it on your CV and then you can give the link and show them, hey, I did a presentation. Your abstracts will go over here. Whatever PowerPoint file you created will go over here. And I'll be putting some additional material over here as well. Okay, so everything you need to, all the data about the presentations, everything is collected over here. For the seniors, your schedule is over here in case you ever forget what date you have to present. Now for the seniors, you guys already did presentations last semester. This semester, you guys are doing individual presentations. Each one of you has to make your own presentation. You have to do all the research, the collation, and the preparation of the slides. And then you're going to do your presentations. Everything else is the same as last time. For the first years, because for many of you, you have probably never done presentations before, your presentations will happen after all the seniors have done their presentations, which means probably sometime in February. Okay, so you've got quite a bit of time before your presentations come over. On top of that, we'll also be dividing you into groups. We'll divide you into groups of maybe 2 or 3 students each, so that you can share the load among each other, and then you can work together. And then sometime in March or so, you will have your set of presentations. You guys are not been divided into groups yet. You have not been scheduled yet. That will all happen later. Let the class size increase, and we'd like to let the students know each other first. For the seniors, everything else is individual. Okay. So before I start, any questions? No? All right. Let me just take a sip of water. Everybody in the department is a member of this, by the way, this Moodle course page, except Sarla. And Sarla, that's because your Moodle account has not been made yet. Once that gets done, once you notify me about your Moodle account, I'll put you in as well. Okay. But everybody is going to be in here. If you can't access it, just remember it says OddSem 2021. If you can't access it, let me know. All right. So what I'm going to do is I'm going to do a very brief presentation. This should not take more than 15 minutes or so. Your own presentations will be between 15 to 20 minutes. So hopefully it'll be just as long. Just let me know if it's coming up on the screen, since I can't see Meet.
It's visible, sir.
All right, thank you. So today I'm going to talk about the phenomenon of inflation in the early universe. Before I start on this presentation, I'd like to just clarify a few things. This is not, because of the time limits and also the background for most of you, this is not going to be an extremely detailed discussion on the theory of inflation. I'm only going to sort of give an overview of the development of the universe since the Big Bang, some of the fine-tuning problems that have occurred, and how inflation kind of is an answer to these problems. I will not be going into any sort of technical detail. In fact, I will not be going into a lot of detail in the interest of time and due to the technical nature of this talk. If you all have an interest in this field, you can always ask me questions about this later, but I won't be talking about it too much. I won't be talking about the technical aspects too much. I've even tried to minimize how many equations I'm going to show. Okay, so I talked about so for the first years, I have talked about the science of cosmology, and I said cosmology as a field looks at the universe as a big picture. It looks at the universe as a whole. We do not look at individual galaxies or individual stars or individual clusters. We are looking at the entire superstructure of the universe. There are a lot of unresolved questions in cosmology, but there are 3 really, really big questions currently. And these are what we call the Nobel questions in the sense that anybody or any group that solves that conclusively gives an answer to any of these questions will more or less have a Nobel Prize named after them. The first one is, what is the nature of dark energy? The second one is, what is the nature of dark matter? And the third one is, did inflation occur in the early universe, and what exactly caused it? I will not be answering the first 2 questions here. I will not be discussing them at all. I will only focus on inflation. These are the big 3 in These are the big three. These are the big three when it comes to cosmology. So before I talk about inflation itself, I'll give you a brief idea, a sort of brief history of the universe, how it evolved from the past to the present day. So historically, what happened was in the 1930s, an astronomer called Edwin Hubble, based on previous published work by other astronomers, most notably Slipher, showed that the universe is expanding, and this was done by him measuring the motion of galaxies that were far away from the Milky Way. And he showed that that every galaxy was moving apart from each other, and that the galaxies that were further away were moving apart faster. We now call this Hubble's law, and this was basically the start of the entire idea behind the Big Bang cosmological picture of the universe. Because the idea is, if the universe is expanding and spreading outwards in time, then if you reverse time, if you go back in time, then the entire universe should have been in a very, very small point. And that is the start of the universe, which we call the Big Bang. Of course, this was not immediately accepted by a lot of people for a lot of philosophical and also physics reasons. People expected a static universe. Albert Einstein, for example, was a very, very famous proponent of the static universe. And it was only a few years after Hubble's discovery that Eddington actually sat him down during a conference and gave his side of the story. He sort of convinced Einstein that the universe had to expand. But the Big Bang phenomenon was basically up in the air. There were debates on both sides until about 1963, or maybe 1967. I think I'm forgetting my dates here, when the cosmic microwave background was discovered. But until then, the whole idea behind the Big Bang phenomenon is the Big Bang occurs, and then the universe starts to expand. Very early on in the universe, and we're talking about 10 to the power minus 36 seconds after the start of the Big Bang, we expect the phenomenon of inflation to occur. Right? It occurs for an extremely brief period of time. I will explain what happened, or like what's going on with inflation in a little bit later. So we have inflation, the universe has expanded massively, and then after a while, your first protons form, the hadrons form, you have the hadron soup, right? A little while after that, so you have to understand, as the universe expands, the entire energy of the universe was concentrated into a very, very small point at the start of the Big Bang. So as the universe expands, the energy density is decreasing, which means the average temperature of the universe is also decreasing. As the average energy density of the universe decreases, things start to happen. So the laws of physics kind of begin to change. After the protons form, a little while later, they start to coalesce together, and our first elements start getting created. This is called the BBN era, or the Big Bang nucleogenesis era. This is when we have the creation of hydrogen ions, helium ions, deuterium ions, etc., etc. Very, very famously started by the alpha, beta, gamma paper. Which reminds me, I'm not going to talk about it now, but later on, if I have time, I would like to talk a little bit about the alpha, beta, gamma paper, because I know a lot of you want to do PhDs, and the alpha, beta, gamma paper is a good case study about when your advisor breaks certain scientific ethics. There were a few ethical laws broken while that paper was written. Okay. After nuclear fission ends, the hydrogen and the hydrogen atoms, sorry, not the hydrogen atoms, the hydrogen nuclei, which are basically protons, are wandering around freely, and so are the electrons, until the temperature drops enough for the protons and the electrons to combine together and form neutral hydrogen. So now we have proper hydrogen molecules or atoms. They are no longer ionized. When that happens, the protons and electrons stop absorbing and re-emitting the photons that are around in the background. They can now stream freely forward in the universe. We can still detect the light rays from that period of time, and we now call them the cosmic microwave background. The reason they call the microwave background was they were very, very energetic photons early on in the universe, but over the billions of years they've been traveling, they've basically lost so much energy that they've gone from basically X-rays and gamma rays down into microwaves. They've lost all that energy, so their wavelength has expanded, both from losing energy and also from the expansion of space-time. So that is the cosmic microwave background. This is the earliest direct detection of the universe that we can make. We cannot detect anything from the universe earlier than this, at least not with our current technology. So everything that we want to know about the early universe, it would have left some sort of an imprint on the CMB. That is why in a lot of cosmological experiments, people heavily study the CMB. There are a lot of long-running, expensive experiments to study this, to study the background. And from there, you extrapolate everything that happened in the past, or you confirm whatever theory you had about the early universe. Even for inflation, we tried to find signs of it in the CMB. After that, we have the dark ages. The dark ages is before the formation of the first stars. All you have is neutral hydrogen. The radiation that is most dominant is the 21 centimeter line of hydrogen. Again, a huge amount of cosmological experiments and telescopes are detecting that 21 centimeter line so that we can figure out exactly what's going on here. Then about 200 million years later, you have the first stars, and then they start forming galaxies. About 9.8 billion years after the Big Bang, dark energy starts to dominate and the acceleration of the universe increases a bit more. And then now we have today's picture, where you can see all of the galaxies, all of the stars, everything being formed. So this is a very quick rundown of the modern cosmological picture from the Big Bang till the present day. And it was a very, very good picture for, and in general, it was a very, very good picture for the explanation of the universe that we observe today. But even back then, even back in the 50s and 60s, there were a lot of questions that there were a lot of sort of uncertainties, some unresolved issues that needed to be explained. And these were called the fine-tuning problems. So what we mean by fine-tuning is that there are certain wide-scale phenomena that we observe in the universe. And in order to explain the phenomena, the conditions on the early universe have to be very, very exact. Any slight deviation in the conditions of the early universe would lead to a completely different universe. So that is called a fine-tuning problem. There are a lot of categories under fine-tuning problems. I'm only going to talk about the big three problems. The first problem is the flatness problem. And the flatness problem was first specified by the astronomer Robert Dicke. He did this back in, I think, 1969. That's when he first published his paper on this. So to talk about the flatness problem, I first need to talk about what we mean by the geometry of a universe. So when we talk about space-time and the universe as a whole, there are basically two opposing phenomena that work together. The first phenomena is the natural expansion of space-time, which will want to expand sort of outwards. The opposing phenomena is the gravitational attraction of all the matter. Okay, so so space-time wants to naturally expand outwards, and gravity sort of wants to shrink everything back together. So these two guys are in opposition to each other, so you can make a ratio between them, which we call the critical density. And that is sort of symbolized by this omega. Now, if omega naught, so if omega naught is greater than 1, it means that the matter is more dominant than the expansion, which means that the universe will expand for a brief period of time, reach some sort of a maximum, and then shrink back down into what we call the Big Crunch scenario. This was considered a possible future for the universe until the discovery of dark energy. And now it is no longer popular, even though there are some theories that still show that it is possible to have a Big Crunch phenomena with dark energy. The next is the opposite of that. When your mass is much lower, has a lower density than the expansion. In this case, the universe will just expand forever. And as time goes on, it will expand faster and faster. So this is the phenomena that is now being caused by dark energy. It has just started in the sense that it started about 4 billion years ago. But over trillions and trillions of years, this is going to be an extremely, the expansion of space-time will be extremely fast. And it can possibly lead to something called the Big Rip scenario, where even the space between the atoms and molecules, between the atoms and the nuclei itself, it can expand so quickly that nucleons and atoms and molecules can no longer be created. Everything will just be like elementary particles extremely far away from each other. So that is the Big Rip scenario, somewhat possible with our current understanding of dark energy. However, at the present time, what we've noticed is that the matter density and the sort of this expansion rate is more or less basically equal to each other. So this leads to something what you call the flat universe, right? Or what we call sort of like a Euclidean surface. So we see the universe is sort of expanding, but it's expanding at a very constant rate, which actually makes a lot of mathematics, at least a lot of the local mathematics when it comes to sort of cosmological stuff, fairly straightforward. And the way we confirmed this was there was a bunch of experiments, famously the WMAP experiment in the 90s, and then the SDSS, the Sloan Digital Sky Survey, which basically did a measurement of the critical density. And the best result we have now is from the Planck telescope. Their latest result is from about 2018. So basically, our deviation from perfect critical density, which is 1, is less than 0.5%. So for all intents and purposes, we are currently in a flat universe. But Dick's question was, if we are currently in a flat universe, what would have been the conditions in the initial universe? Right, right after the Big Bang, what should have been the conditions of the universe that allows a flat universe in the present day? Okay, if we extrapolate backwards in time, what kind of conditions would occur? And that's where we lead to the fine-tuning problem, because according to our best knowledge, during the Planck epoch is basically 10 to the power of minus 43 seconds after the Big Bang. Okay, so this is immediately after the Big Bang. The deviation from perfect 1 has to be less than 10 to the power minus 64, less than the order of 10 to the power minus 64. To give you an idea of how stringent this condition is, let's say you're constructing a shopping mall, and because one molecule of one brick was out of place, the entire shopping mall is going to collapse. You cannot construct a shopping mall. Okay, imagine you're constructing a shopping mall, a huge structure, and because one molecule of one brick was out of place, the shopping mall will collapse. That is something like the condition that we have over here. If their density changes even slightly, even the tiniest bit, we will have either a fully closed universe or a fully open universe. We will not have a flat universe today. However, there is an argument against this, and the argument is at the Planck epoch, quantum gravity dominates. We do not have a good idea of what quantum gravity is like. This is a huge open problem in physics, probably the most important open problem in physics, the nature of quantum gravity. So we can be like, since we don't understand quantum gravity, we cannot really trust this limitation. And we'll be like, okay. But during the Big Bang nucleosynthesis epoch, so this is between 10 seconds to 3 minutes after the Big Bang, this is extremely well explained by our current knowledge of physics. There is no exotic physics going on over here. This is an extremely well-known phenomenon, this is a very extremely well-known epoch and can be perfectly explained with our current knowledge of physics. Again, there the deviation of the critical density from perfect 1 is of the order of 10 to the power minus 16. Now, let's say you're not constructing a shopping mall, you're constructing like a 3-story building for your family, and one molecule is out of place from a brick, and then the whole thing collapses. It is still an insanely stringent condition. And the fact that any slight deviation would lead to an open or closed universe kind of makes it seem that this is, the theory is not solid. We should have an explanation. We should have a very, very reasonable, a very good explanation as to why the universe is flat. So that is the flatness problem. The next problem is known as the horizon problem. And it was first talked about by Wolfgang Rindler back in 1956. The horizon problem is basically, we have something called the cosmic horizon around us. The cosmic horizon is sort of the furthest extent that light has traveled from us at the center. So if you imagine like a sphere around you, so imagine this is the sphere around you, and you can imagine like a circle around you. This is the extent, if you are at the center, this is the extent of light that has traveled so far. Based on our current understanding of physics, light is the fastest thing that can travel. So if something exists outside of this sphere of light, it cannot affect us, and we cannot affect them. Okay. So what we say is we live in a causal patch, and there are various causal patches in the universe. Now, obviously, as time goes on, this light will expand further and further, and we will be seeing more and more portions of the universe that we could not see previously. All right. So as the universe expands in time, we come into contact with other areas of the previously unobserved universe, and that we can now sort of interact with. We can see light from there. And the problem that Rindler pointed out was that why does the universe have the same temperature, the same matter distribution, and the same density everywhere that we look? On a very, very large scale, no matter how far away or in what direction you're looking at, the background temperature of the universe, the matter density of the universe, and also sort of the physics of the universe is exactly the same. We have not seen any large-scale deviations, which kind of does not make sense, because if you can see, these are all causal patches which are sort of independent of each other. There is no reason for them to have the same temperature or the same matter distribution. In fact, people have done the calculations and they've shown that in the early universe, there should have been 10 to the power 6 causally disconnected regions. This is a really large number. So the way of thinking about it is, because of the nature of the second law of thermodynamics, the nature of entropy, you want as much disorder and as much random arrangement as possible. So you want all of these causal patches to have, the natural phenomenon is all of these causal patches will have different temperatures. Okay? If they have different temperatures, and as we sort of come into contact with them as the universe expands, we should be seeing all sorts of different temperatures at different parts of the universe. But we don't. Everything seems to have basically a constant temperature. So this was the horizon problem. Again, unresolved at that point of time. The third problem that I'm going to talk about is known as the magnetic monopole problem. So we know what an electric monopole is. Protons, electrons, these are single units of charge, either positive or negative. Magnets in nature do not come in monopole form. They come in dipole form, in the sense that the magnet will always have a north pole and a south pole. And if you break them apart, like if you take a bar magnet and you break it apart, the ends will also become the north pole and the south pole. You always have a north pole and south pole. You can go all the way down to the atomic level where an electron is rotating around a proton. That will create a north pole and south pole. But if you move the electron and the proton apart, well, the magnetic field just disappears. So the magnetic monopoles don't, at least for now, they don't exist. However, in modern physics, especially since the development of quantum mechanics, we expect magnetic monopoles to exist. We expect there to be elementary particles which behave like a magnetic monopole. This was famously started by Dirac's 1931 paper. This is an incredibly famous paper. If you guys do a master's in physics, you'll most likely read this. He explains how electric charge is quantized. So electric charge has a minimum value of 1.6 times 10 to the power minus 19 Coulomb, positive or negative. That is quantization of electric charge. Dirac shows in this paper that the electric charge will get quantized if magnetic monopoles exist. It is a very famous paper. Has some issues, but quite brilliant for his time. And later, two physicists independently, one of them was known as Gerard de Hooft, who later won a Nobel Prize, and another was a Soviet physicist called Polyakov. They both independently came up with the idea that in high energy physics, magnetic monopoles should have been created. It is a necessity as a development of the high energy physics. It is a necessity in the development of the combination of the strong force and the other forces and with the electroweak interaction. So because of this, at least in high energy physics, we expect, at least with the current knowledge of physics and the current confidence in the various theories of physics, we expect that magnetic monopoles should exist. And Preskill in 1979, and basically Zeldovich and Kolopov, and then later Preskill, showed that in the early universe, the conditions were perfect for the creation of magnetic monopoles. And Preskill even showed that magnetic monopole should have been created in a massive amount. As he says here, the density of such a monopoles in the early universe is estimated to be unacceptably large. So monopoles should have been created sometime in the beginning of the universe, but we have never detected them. Where are all the magnetic monopoles? Why haven't we detected any of them? Okay, so that was another huge open question. So these are my three fine-tuning problems, or at least the major ones. So in the 1970s, there was a conference going on, I would say in Cambridge University, where a bunch of astrophysicists were sort of discussing some of these fine-tuning problems. Famously, Stephen Hawking was also there. He actually talks about it in A Brief History of Time, if I remember correctly. And in that conference, a young postdoc by the name of Alan Guth came up with the idea that we now call inflation. And all of them were quite taken with the idea, and they worked on it, and then it developed from there. So before I talk about inflation, I'm just going to talk about some of these more technical terms here. The scale factor here is basically something that tells you how quickly space-time could sort of characterizes the expansion of space-time. If it's positive, space-time is expanding. If it's negative, space-time is contracting. And then we have something called the Hubble parameter, which tells you how quickly that scale factor is changing. Basically, as the universe expands, your scale factor will increase. As the universe contracts, your scale factor will decrease. What Guth what Guth's idea in inflation was that very, very quickly after the Big Bang, the universe had an exponential increase in its expansion. And that's why we have a e to the power this. The expansion of the universe was exponentially fast. This is called the de Sitter expansion. And with all of the work that we've done, we expect it to have started 10 to the power minus 36 seconds after the Big Bang. This is an incredibly tiny period of time. To put it in perspective, the shortest period of time that we have measured with our instruments, that we have measured with our instruments, is something like 10 to the power minus 21 seconds. And this is like so much smaller than that. So it started around here and then ended around 10 to the power minus 33 to 10 to the power minus 32 seconds after the Big Bang. And in this time, the universe expanded by a factor of 10 to the power 26 or e to the power 60. To give you an idea of how quickly this expansion is, imagine you have a balloon that is the size of a bacterial cell. And then in this period of time, it went from the size of a bacterial cell into the size of the Milky Way. Okay, so something that was originally the size of a bacterial cell blew up into the size of the Milky Way. That is a factor of 10 to the power 26. Realistically, after inflation, I think the actual observable size of the universe was something like roughly the size of a football. But that is how much of an expansion that happened. So why do cosmologists care about inflation? How does it explain the fine-tuning problems? Well, it actually fixes all the three major problems I talked about. The thing about the flatness problem is so I just like you to visualize. Think of a balloon, okay? A very good way of visualizing the expansion of space-time and all of this inflation phenomena is to think of a balloon like being filled up with air. Before the balloon is inflated, it's all wrinkly, right? It's wrinkled, it's got all of this little creases and stuff like that. But when you blow it up with air, it expands and everything becomes nice and smooth. All of that inhomogeneity, all of those different densities in the balloon, they all get smoothed out and equalized. Everything is equally distributed. That is the same thing that happens in inflation. In inflation, because the universe blows up so quickly, blows up so much in such a short period of time, it forces the universe to become flat. See, if inflation happened, you will end up with a flat universe. So so this kind of explains why the universe is flat today. Why is it flat today? Because possibly inflation happened in the past. How does it solve the horizon problem? Well, let's say before inflation, you have all of these different regions of space-time that are connected to each other. Okay, so because they're connected to each other, they have the same temperature, they have the same matter distribution, and they have the same, well, it's not matter then, it's like energy. They have the same energy distribution. They also have the same physics. And then inflation happens, and then everything gets spread apart very, very far. The inflation happens, the expansion of space-time is so much that different regions of space that were originally in contact with each other and originally were in equilibrium with each other, they are now spread so far apart that even light, they are completely in different causal regions. But over time, after inflation, as the universe naturally expands, these regions come back in contact. But because the physics was already the same, the initial temperature was already the same, it is not a surprise for us to see that they are exactly like the same as our causal patch. So that sort of explains the horizon problem as well. We are simply reconnecting with areas of the universe that were previously connected to us before inflation. And finally, how does it explain the monopole problem? Very simple. Monopoles were created before inflation. No new magnetic monopoles were created after inflation. So monopoles are created, inflation happens, the monopole density is completely decimated. Currently, the best estimate we have, there's an experiment in Antarctica, it's called Ice Lake, yeah. So from the best estimate from Ice Lake, we currently have one monopole every 10 to the power 29 nucleons. So the reason we don't detect monopoles is because they're extremely rare to detect. The density is extremely low. To give you an idea, I think it's like one monopole every 10 cubic light years, which is, it's just, you're not going to detect an elementary particle that is this rare. Why isn't matter similarly widely distributed? Because the creation of nuclei and all happens after inflation. In fact, at the end of inflation, there's something called reheating, which is caused by something called parametric resonance. And the phenomena of reheating basically creates baryons and leptons. Okay, So this is what. So there are many other. There's a lot more going on to inflation. I haven't talked about the models of inflation, the classic inflation model, slow roll inflation, then the modern models like chaotic inflation, eternal inflation, hybrid inflation, things like that. But for now, I think I've even gone over time. So I'm just going to end things here. Inflation is one of the biggest one of the biggest theories in cosmology, and a lot of effort has gone into trying to prove that it occurred. It's basically like how the Higgs boson was for particle physics. This is our theory. This is a theory everybody believes in. We just need to prove it conclusively. So that's it for my talk on inflation. Thank you for bearing with me. These first two is where you can sort of get a background for inflation if you're interested. If you'd like to know more, I would recommend you these two sources. One is the Wikipedia page on inflation, has a pretty good sort of introduction to the whole thing. And 60 Symbols, which is a channel on YouTube, excellent channel on YouTube, by the way. They have a nice video on inflation by Professor Merrill, I believe, or Merriweather, who is a cosmologist. And he gives a very good talk about inflation as well. So both of these can be up your alley. So thank you very much. And I'll take any questions that you may have. Am I still online? Everyone's very quiet.
No questions. We had so many aspired astrophysicists.
Okay, so Anajat, you said something about inflation presentation against Einstein. Is that a question or just a comment?
No, sir. It's only a comment.
Okay, just a comment.
When you are talking about this.
Okay. I forgot who asked me this. I think Rajal said it might have been you. You asked me about the flight path of EBEX in Antarctica.
Yes.
This is the
Yes.
flight path. I managed to dig up the
Let
picture.
me see. Achha.
So around here is McMurdo Bay, and we launched it around here. And then this is the path across 11 days, and I think it crashed somewhere around here.
Oh. So
It is only a
crash does
14-day
happen.
flight.
So crash does happen.
No, like you cut off the balloon and there is a parachute, so it does parachute down.
Oh, okay.
But you have to bring it down sometime. It's an 8-ton instrument, so you have to bring it down sometime. And all the data is on the tapes. The backup tapes are on the data, so we have to recover it. Actually, they had a tough time recovering it. Also, somebody almost lost their toes to frostbite.
Acha, I see. And the air is also very thin, very challenging, no?
Yeah, here at least over there, it was very challenging because it's in the middle of nowhere, and it's very cold. And they had a hard time. Like just two of them went to recover it. I think there was some Australian team or something here who helped them out.
Correct. Very interesting.
Okay, does anyone have questions about the thing? Okay.
So you mentioned like a small time interval, right? 10 to the power minus 64 in your I think second slide or third slide, I guess.
This will be the Planck time.
I think Planck time is 10 to the power minus 44, right? If I'm right.
Minus 43. 10 to the power minus 44. The Planck epoch is up to 10 power minus 43. Actually, I had a table. So here's the Planck epoch.
Yeah.
This is the first epoch after the.
So, but in your slide is 10 to the power minus 64. What is that actually?
Oh, this is the order of the deviation between the critical density and 1.
So it's the order.
It has to be, the deviation has to be less than this order. Otherwise, we do not have a flat universe.
Yeah. Order of what? I mean, like unit?
The critical density is dimensionless.
Okay.
It's a ratio.
Okay.
It's called the critical density, but it's actually a ratio of like the matter density and sort of the density of the expansion. So it is technically dimensionless, but its deviation from 1 has to be less than the order of 10 to the power minus 64 for us to have a flat universe that we see today.
Okay. Okay, sir. Thank you.
Okay, thank you.
No questions from students? All are very quiet today.
Okay, I can see Sonajit's comments, so that's fine.
Acha.
All right. Okay, cool. There are no questions. I can skip this. Now let's go to the part that actually matters. This is just a demo class. The part that actually matters is how do you make a presentation. That's the entire reason why we're doing this. This is just a demo of a presentation that you can sort of to give you an idea. When you make a presentation, there are 3 parts. All right. Let me start this. There are 3 parts in preparing for a presentation. First, you do your research. You go on Wikipedia, you go on YouTube, you look at your textbooks, you look at articles, you read the newspaper magazines, whatever you think, whatever you want to approach, you start from it. For this inflation presentation, the first place I go is Wikipedia. I read up to find out the articles on it, and then I went to the textbook that I mentioned in the background, the book, the textbook on cosmology. Once you do your research and you collect your materials, you want to do a collation. Collation means that you pare down whatever you want to put in. You basically do a rough outline of your presentation. You decide how many points you want to talk about, because you guys have only 15 to 20 minutes. So you'll have to estimate how many points there are. You select only the material that is important, and then you sort of construct your speech, okay? So you will have an idea of what the slides are, how you make the speech, what points you're going to talk about, and what points are not important. Finally, you do the construction, where you actually make the presentation. There you make the slides, you decide which topic goes on which slide. You put in all the either the GIFs or the images or the videos or the graphics or the tables or the graphs, whatever that you need to put in to make your point. You put all of that there, and then you do a revision of your speech. Okay, so these are the 3 parts in making a presentation: research, collation, construction. I think somebody had a question. Okay, see you, sir. Sir has to join his own orientation as a new faculty member. So, for example, what I mean by 1 topic per slide, let's have a look at the fine-tuning one. The only thing I talk about on this slide is the flatness problem. The only thing I talk about this slide is the horizon problem. Even though I have some space here to fit something else, I don't use it. The only thing I talk about this slide is the magnetic monopole problem. You want each slide to only have 1 idea. You can share ideas across slides. For example, all 3 of these do talk about the fine-tuning problems, but you just want to limit 1 idea to 1 slide, nothing more than that. How many slides should you make for a presentation? In general, not counting the title slide and the thank you slides and all the reference slides, not counting all of these slides. In general, you only want, in general, each slide will take roughly 3 minutes. So if you have like a 15-minute presentation, you probably want 5 slides, and then your title slide, your thank you slide, and your reference slide and things like that. So that is a decent estimate. How many, like depending on how much time you have, you sort of estimate 3 minutes per slide. Sometimes it'll be more, sometimes it'll be less. For example, on this slide, I only spent like 1.5 minutes or something. But on this slide, I'm pretty sure I spent like 5 minutes because there's quite a lot of material to talk about. So it can vary. It'll depend upon your speech and how you prepare, but that is a decently good estimate to start with. Another thing about a slide, do not clutter up your slides. Do not put too much information on your slides. For example, if I had presented your slide just like this is way too much information at once. So what I do is I make the use of animations. So I'm going to wait for this slide to load. Okay. And then I use animations. I press the key once, you see a little bit of the information. I talk about a rocket dick. I press another key, and now I talk about the geometries of the universe. I press one more. I keep pressing buttons, and then I show the information 1 point at a time. If you have a lot of points to make, try and use animation so you show only a little bit of the picture at a time. This way, you do not overwhelm your audience with too much information at once. Okay, you don't want like a full table. Like for example, if I present this table like this. Okay, we have to wait for this thing to load. Hold on. Yeah, if I present you a table like this is too much information at once. Okay. I decided to cut this out, that's why it's like this, but I would never present like a table like this. This is way too much information all at once. You want to use things like animations so that you only show like little bits of information at a time. This way you can keep attention and people don't get like distracted with all of this writing. All right, so that's one thing. Do not clutter your slides. Again, last semester, some of you had some very, very nice, very intricate like sort of borders on your slides. Make sure that the border is not more distracting than the material on the slide. That is again not a very good thing. And aside from that, I would highly recommend you just use Google Slides if you're making a presentation. You can use PowerPoint also. You can also use LibreOffice, which is what I tend to use sometimes. But the nice thing on Google Slides is if you have to transfer slides back and forth between computers, Google has a universal format. As long as you open it in Google Slides, all your animations will carry over, everything will carry over. You can't guarantee that with PowerPoint. I once made a slide in PowerPoint 2007, and then when I presented in PowerPoint 2013, everything was out of place. So that can happen. Next thing you should know, you'll notice that I do label most of my pictures, and I always give credit to where I take the pictures from. Please do that. Always credit your sources. Very, very important. Even here, you can see the credit. Okay. Unless, of course, I'm the one who created the pictures. In that case, I don't bother crediting. And in your references, this is very important, especially for the second and third years. Please follow a formatting style. My recommendation is the APA formatting style, right? All of these things are formatted according to the APA style. You're supposed to, as a scientist, when you're giving a scientific talk, when you put references, they have to follow specific formatting styles. The APA style is very, very common. Otherwise, it's the AMA style. The APA is the American Psychological Association. The AMA is the American Mathematical Association. I have a website here which tells you exactly how to format your references in the APA style. You want to format something, you want to talk about some YouTube video that you referenced, here we go. This is how you format the YouTube video. You went to Wikipedia and you want to sort of reference a Wikipedia page, well, right down here. Here you go. This is how to reference the Wikipedia pages. You want to reference a textbook, it's all over here. Books. Okay. So just see what kind of book you have, and we have all the formatting styles necessary. Get used to it. This is something that is expected from a science student, the ability to format things in the correct citation style. And in most cases, if it's a book or a journal article or something like that, the easiest way is you go to Google Scholar. Okay. And let's say I want to cite a textbook, University Physics by Young and Friedman. This is a very well-known textbook. So I do a search for it in Google Scholar. And you'll notice there's a search bar here. What you do is, so I want the 2013 version. Okay, this one. Right over here where you have the double quotation mark. If you hover over it, it says cite. Click on it, and here you go. Here it is, nicely formatted in APA style. Just copy and paste it on your slide. Okay, this works for books. This works for well-known books, scientific papers, anything like that. You can easily get the formatting over here. Won't work for YouTube and Wikipedia articles. For that, you actually need to read this and then format it that way. But it's not that big a deal. As you can see from my slide, formatting it is fairly straightforward. And finally, I'm going to talk about the abstract. The abstract usually uses a specific language. What your abstract would be should be like a short paragraph explaining the basic points that you're going to cover. You notice that I used the word we. By default, not always true, but by default, we use the passive plural. Okay, so we use the word we. I basically say that I'm just going to talk about the expansion of the universe, fine-tuning problems, and then how inflation resolves those issues. It doesn't have to be extremely detailed. It doesn't have to be extremely long, but it needs to be a short paragraph explaining so that when somebody reads it, they know what to expect out of your presentation. It cannot be like a list of points or something like that. I don't know if is Priyam in the audience? Yeah, Priyam. So Priyam, your abstract is sorry. So Priyam, you gave me a list of points. It needs to be written as a paragraph form. Okay. So I would like you to rewrite your abstract now that with this in mind. The reason writing the abstract is important is because later on you might be taking part in conferences or things like that. They will always say, so please submit an abstract first. And if your abstract is not, like if it's too long, if it is not very clear about what you're submitting, they will just straight up reject your paper. They will not let you like present in the conference. So get used to the idea of writing abstracts as well. Okay. I think I covered most of the important points that I'd like to make. Maybe Prajwal sir or Sujata ma'am could add anything that I might have missed out.
Nothing from my side, sir.
Am I audible?
Yes, Prajwal sir.
Yes, sir. So your microphone is not audible if you are speaking. Still not audible, sir.
Am I audible?
Yes, sir. Now it's audible.
I'm extremely sorry. This by default the setting is changed continuously. I do not know why. Yes, I thank Vikram Ditsa for his wonderful presentation, and I hope the students have surely gained insight of what they are, how they are supposed to present. So first of all, so yeah, as you may all have noticed that Sir's slide, whatever he presented, it was not messy at all. Okay, so you are required to put as less text as possible. Okay, and more figures are encouraged to be put in the slides. The idea behind this is that you want to grab the attention of the audience. Okay, so if there are many audiences and if you are not able to get hold of any one of them, then there's no point on presenting your presentation. So that is the main objective. Okay, so you're kind of making an advert and selling it to the customers. So if you want to grab a hold of the attention, you have to abstain from using too many texts. So that is one of the criteria. Another is to use as many figures as possible, and also yes, giving credits to sources. Like if you are taking some material from let's say Google only, okay, if you are using some of the images. So if you do not find a proper source, you are required to provide the address, HTTP address that you have used for that particular picture or maybe or other type of materials. Okay, so crediting a source is very and it's an integral part of making a PowerPoint presentation. So as a professional and as a physicist and as a graduate, you should be able to know these elementary things, basic things. And apart from that, so our I'd just like to announce that we are having our student presentation session from the next Saturday onwards, that is 18th of September 2021. Okay, so from there on we will be continuing. As of now, we will be having presentations from second and the third years. Okay, once they are over with their sessions, then we'll move ahead with the first year. So in the meantime, why we have done this is that we could have put first years in the beginning also, but the thing is that we want all the first years to get used to the slides and the presentations that your seniors make. Okay, now your seniors are much acquainted to present themselves. Okay, so present their slides as well as present themselves. So you are not only developing your writing skills and your presentation construction skills, you will also be able to have this customary towards speaking out in the public. So this is an integral part of your professional development. Later on down the line, when you apply for jobs or do some kind of a intern, you are expected to know all of this, and you should be by the time comfortable while presenting yourself to the audiences or to the companies. Okay, so here also at some point of time we see that you find some of the even the seniors, they are very reluctant to unmute their mic and speak over the meeting session. Okay, so I humbly request you to kindly develop the skills. It's with time you will learn. Okay, it's not just not just magic. It takes time for you to get acquainted with the system and then confront the audience to how to tackle the questions, tricky questions. All these skills you will be learning in due course of time. So when you participate, like we have in this coming Saturday, Priyam and Aryanjali, they are presenting. Okay, please give enough time to prepare for your presentation. Okay, so this will all in all help you in the long run to be a professional in terms of delivering the output to the audiences. Okay, so even if you later on down the line, if you go to the teaching profession, this will definitely be helpful. It doesn't mean you have to do the teaching and give presentations. So technically what we are doing, we are developing your communication skills. Okay, so everything is like included in this student presentation session. So please take this seriously. It will be you'll have the overall benefit of all the skills that that a presentation personnel requires. Okay, so and then once the first and third years are done, we will move ahead with the second and third years are done, we'll move ahead with the first year. So during this presentation session, we expect all of you to kindly attend. Okay, it will not take very long. So every Saturday we'll have it between 9:40 and 10:40. So kindly be make yourself available until and unless it's very necessary for you to skip the session. Okay, so no other department, I don't think, I'm not boasting, but I don't think no other departments are having this sort of activities with their students. Okay, so kindly please take the best use of this platform. All right. So with this note, I'd like to end my speech here, and thank you so much, Vikramjit sir. Over to you.
Thank you, sir. I think BBA and BCom do presentations, but that is actually part of the syllabus.
Acha.
I think it's part of their training. I think they have it there.
All right.
But we don't need to do it. We're just doing it because it helps. So I won't drag you out long. I know that it's lunchtime for most of you, and you're tired of, and I know most of you are tired of listening to me. The only thing I'd like to mention is, as you can see, I'm not that great a speaker, and neither am I great at making presentations. Some of you might have been like, I can do such a better job. If you can do a better job, please do so. We would love to see great presentations. What I do want to say is your presentation doesn't have to be mind-blowingly awesome. You don't have to be a great speaker. You just have to be competent, and you sort of need to have an idea of what you're doing. Okay. In the Enactus presentation today, Diksha was actually an extremely good presenter. You noticed how much energy she had in her voice, how she was interacting with the chat, the intonation that she was using. That is an example of a very good presenter, someone who I would consider is much better than me in talking in a presentation. So that is a good ideal to sort of like try to be. But all you need to do is be competent and understand what's going on in the presentation, have a good idea of what's going on with your presentation. The next thing I'd like to say, I wanted to say one more thing, and I think I've forgotten. Okay, never mind. It'll probably come back to me later. Everything that I presented, the abstract, the slides, the link to the website that will tell you how to do the citations, I will put all of that on the Moodle course page so that you can access it. All right. So everything will be, the record will also be up. Everything will be up, so you can always access it from there. Okay. If there are any questions, I will take them now. Otherwise, you guys can feel free to log off.
Sir, about Monday, at what time we have to report?
I will have to talk with, we'll be talking with, you're not the only department that's coming. There are other departments coming as well. We will be sort of talking with them, and then I'll get back to you. Assume it'll be either 9 a.m. or 10 a.m.
Okay, sir. Thank you, sir.
I know some of you might be coming from the hills and might be late. We'll work around it. I'll be sending some messages after this.
Thank you, sir.